right, so now, what we did is that we looked at the unilateral system, and we saw that you could generally define a loop gain that was invariant of a single loop if you had a single loop. And it basically had the property that you could calculate it anywhere. We also saw a good way of calculating this, which made it easy not to think about the loading effect. We saw that in practice that in circuits you have currents and voltages. And what you want to do is that if you don't want to worry about what is the loading effect of this network on that network, how much load my feedback network represents, you can break the loop anywhere. And as long as you calculate two quantities, a forward loop voltage loop gain and a forward current loop gain, you could quickly saw that you could calculate the overall loop gain from this expression, which basically said that the overall loop gain, forward loop gain in a unilateral system is 1 over that, is 1 over the voltage loop gain plus 1 over the current loop gain. So you can actually calculate these two quantities and easily determine that. So that was for a unilateral system. Now, in a bilateral system, things become a little more complicated. In other words, bilateral system is in which the signal can travel in both directions in both of these boxes. So in other words, you have a dependent source on this side that will drive that and vice versa. So if you have something like that, a more general two-port box, then the question is, how many of these quantities do you have? Obviously, you have the quantities that we discussed. Let's say the desired loop direction is in this direction. Now, you could determine the voltage loop gain. We call this the forward voltage loop gain. And you could determine the current loop gain by doing this. So these are the forward voltage and current loop gain. So this is TFV, and this is TFI for forward. But now, unlike before, if I actually apply a test voltage to this end, let's say I put a voltage source here, let's call it Vy, but it's now a voltage source, and measure Vx, Vx would be non-zero if I have it, in general, if I have a bilateral loop, right? Because now the signal can travel backwards in these two boxes and come back. So in general, I have both directions of signal flowing. So then, based on that, I can determine a reverse loop gain, which would be a modification of what we had for forward. So here, before this was the forward loop gain, now I can determine the reverse voltage loop gain. Well, let's do it. So now T reverse for the voltage, TV reverse. In our notation, you say TV reverse or TV? Yeah, TV reverse. Okay. So it's the voltage loop gain in the reverse direction. It's defined by definition as Vx over Vy to the minus sign when Ix is 0. You see, this is very different. Although it looks kind of similar, this Vx is very different because this Vx is not being driven. This is a different network with a different input and a different output. So now, instead of driving this node and looking at what voltage comes back here, I'm driving this node and looking at what voltage comes back here. So this is a completely different calculation. It's not 1 over that or something like that. Because they're driven at different nodes. And similarly, you can do the same thing for the currents. So you can actually say, I put a current source here, Iy, and measure what comes back, Ix. And in this case, Ti reverse is defined as Ix over Iy, when Vx is 0, meaning the X port. This port is short. Remember, because before Vy was 0. So it's different. You short this port. So it's exactly the opposite of that. I want to say how much signal flows in this direction and how much flows in this direction. This is the forward direction, this is the reverse direction. So in general, we'll talk about 4 calculations. However, it turns out that one of them is redundant when you do the calculation. Okay. Now, I'm going to actually tell you what the result is first, and then we'll derive it with the derivation. This way, at least you know where we are going. So it turns out that if you have a bilateral loop, this equation will be modified. So now you have a general bilateral loop. have improved against what we will, is that TB forward times T times TB reverse is equal to TI forward times TI reverse. Namely, the product of the forward and reverse voltage gain is the same as the product of the forward and reverse current gain. Always. And we'll prove this. So I'll just tell you what the result is. This is the result. So you see there's a third correction term which is defined in terms of one of the reverse loop gains. So if you want to do it exactly, all you need to do is determine one, whichever one is easier for you, of these reverse loop gains. If you determine one, you can actually plug it in this equation. This is exact. So it's a minor modification to that essentially. So now, how do we prove that? Let's do that. So let me know what happens. Okay, so now let's go back to this picture that we started with unilateral. Make it bilateral. How do I make this bilateral? I have to put two sources, right? Two current sources here and there. So this would be G4 VI, and this would be G1 VO. General case. So now, one thing that we said before, you remember in the beginning of our discussion here, we said whatever this loop gain is, has to satisfy this. In other words, the poles or the roots of the determinant of the circuit has to be the same as the roots of the 1 plus t. Otherwise, your transfer function will not match. I mean, you will not have the same transfer function. Now, this doesn't give you a unique t. There are many t's that satisfy this. But you have to make sure that this actually is valid. So, how do we do that? So first, let's determine the transfer function of this. Okay. So if you represent this as a whole thing, let's just erase this stuff. So let's do it. So let's write the equations here. In general, if this is IN, what does the KCL on this node tell me? It tells me that y1 vi, or y1 plus y3, these are in parallel, right? y1 plus y3 vi plus g1 plus g3 vo is I or equals to minus I inside. Right? Because these three currents, the sum of the three currents has to be, oh no, actually it's equal to 1, right? But this going in is equal to 1. And then, on the output, let's just put it up on the output. No, I have y2 plus y4 times VO plus, or let me just break this. y2 plus y4 VO plus G2 plus G4 VI is 0. And you can see that basically I can write it in terms of the Y matrix, right? So I can write this as Y matrix times the voltage vector is equal to the current stimuli IA, where Y is YI, YO, GI, GO. So I define this as GO, define this as YO, G, this is GI, this is GO, and this is YI. So it's basically a matrix representation of that. So I'm basically saying G1 plus G3, G2 plus G4. Okay? So that's what it is. Now, one thing that I want is that now I want to determine the forward loop gain. Current and voltage loop gain in this case. So I need to break this loop and do it two different ways. Calculate the forward current and voltage loop gains. So Vx measuring Vy, and let's do it here. So let's do it here. So say, so what's that? You can write the equations for that. You can write a set of equations, and then just do it for one, and then we'll use the results for the rest. So in this case, if that's Vx, what do you know about the V? In this case, this is Vx. This is going to be Vx. Okay? And therefore, you know that the currents at the input are, and this is in the absence of an input perturbation. So you know this current plus this current plus this current plus that current is 0. So meaning that G3 Vx plus G1 VO plus Yi Vi is 0. That's one set of one equation. And then here you have another equation, which is simple. So basically it says G2 Vi plus Y2 Vy is, oh, this is also Vy, right? Vy is 0. So all you need to do is to eliminate Vi between these two equations. So Vi from this one is minus Y2 over G2 Y. Plug it into this guy. So you get G3 Vx plus G1 Vy is basic algebra. Minus Yi Y2 over G2 is 0. So divide by G3. And then move it to the other side. So you get Yi Y2 over G2 G3 minus G1 G2. Vy is Vx. And therefore TFV, the forward voltage loop gain, by definition Vy over Vx is going to be minus that. So you can write that minus G2 G3 or let's just write it as G1 G2 minus Yi Y2 G2 G3. Let's double check. 1 over that. Oh, yeah, that's right. That's up. So it's going to be minus G2 G3 over Yi Yo minus G1 G2. Right? So that's how you do it. So we can do 4 sets of these equations, which doesn't add a whole lot to our knowledge. And the equations are there in your handout. If you're interested, but I will give you the results. Okay? So let's do it. So this, if you do the similar thing, so basically now if you were to calculate the forward current gain, so we are doing the derivation. So you put an Ix here and measure Iy. And if you write the new sets of equations, what you will see is that your T, the forward current gain, is going to be minus G2, G3, Yi, Y4. Actually, this one was Y2, right? Yeah, Y2. Y4 minus G3, G4. Fine. And then the question is, let's see 1 over Ti plus 1 over Tf, Ti plus 1 over Tv. Does it give me the loop gain? So let's calculate that quantity. let's calculate 1 over TFB plus 1 over TIB. Because we knew that TFI. We knew that that worked in the unilateral case. Let's see if it still works. So if we do that, basically they're adding the reciprocals of these two. They have a common denominator, G2, G3. Is that denominator? One over this and one over that. So what is left here is that you get yi, y2, yi, y4. So you get yi times y2 plus y4, which is yo. So you get minus yi, yo, minus this, minus that, minus G1, G2, minus G3, G4 over G2, G3. Fine. But now let's look at delta. This is kind of close to delta, but it's not exactly delta. Can I write it in terms of delta? So delta has two extra terms, if you look at it. I have G1, G2, and G3, G4. So I have G1, G2, and G3, G4. But delta also has a G1, G4, and a G2, G3, right? So is it fair to write this as minus delta plus G2, G3, those extra terms, G1, G4, over G2, G3? The question is, does this qualify as 1 over loop gain? Can this qualify as a reasonable loop gain? Now, for it to qualify as a reasonable loop gain, we have to have what? We have to have that if t is minus 1, it should be equivalent to having delta of 0. So in other words, they have to have the same roots. 1 plus t should have the same roots as delta. Can we say that now? Is this true? Think about it. If delta is 0, this is what? This is minus 1 plus this G1, G4 plus G2 over G2, G3. We have one term too many, right? If I didn't have this, this would be alright. Right? Because if t is minus, if delta is 0, t is minus 1. Because if delta is 0, it would be G2, G3 over G2, G3 with the minus sign is minus 1. So this is my error term. So this is something that I have to correct. So basically then I say, okay, if that's the error term, then my t should be, so my t, if that were to be correct, then it has to be minus G2, G3 over delta plus G2, G3. Right? To make this happen, I have to add one term to this sum. What is that term that I have to add? So let's say 1 over t forward, the forward loop gain, this is the forward loop gain, is going to be 1 over tf b plus 1 over, tpf, so tif plus, I have to do something to fix this, right? What do I need to add to this to make it equal to that? This term, right? This last term. So it has to be minus that. It has to be basically, or plus, so G1, G4 over G1, G2, G3. So this is my correction. Now, it's useless in its form, in this form, because it means that I have to reduce everything to G1, G2, G3, G4. But fortunately, it can be written in terms of the reverse loop gains. How? Well, let's calculate the reverse loop gains and see what they are. So let's do that quickly. Or let's show you how we do this, essentially. So it's a very similar procedure. If you want to calculate the reverse voltage gain, what you do, you've opened it here, but now you apply a voltage source here. So you apply a Vy here and measure Vx. And if you do that, you get basically a TVR, the reverse voltage loop gain, which you can calculate. You are writing the set of equations that we have. y I y2 minus g1 g2. Okay? So that's what we have. So we have four quantities. These four quantities. And if you look at them carefully, you will see these two and those two. You see that if you calculate the products, what you have is that you have T V forward times T V reverse is equal to T I forward times T I reverse. You will see that. And furthermore, what you see is that this term is simply Ti reverse over Tv forward, which is equal to Tv reverse divided by Ti forward. And by the way, this term is interesting, right? Look at it. Tell me what condition needs to hold for it to be zero, for it to reduce the previous case. If either G1 or G4 are 0, our calculation would be correct, right? And what does that mean in terms of the circuit? Right. So one of the reverse gains are 0. One of these gains are 0. If one of them is 0, what happens is that the signal cannot travel in the opposite direction. You either kill it here or there. And as a result, your loop is unilateral, which means that for unilateral loop, you have the correct result. And then for bilateral, it's basically this expression that we derived earlier. So there's a correction term. So what you need to do is to calculate one of the reverse loop gains and the two forward loop gains. So this would be Tv forward, Ti forward. And this would be Tv forward, and this is I reverse, or V reverse divided by I forward. So, makes sense again in this term too. If you have no reverse loop gain, namely you have a unilateral loop, this disappears. It reduces to, that's the way to remember it. It has to have a reverse term here, because it has to reduce to that original result if there's no reverse gain. There's no reverse loop gain. And it's the other way to remember in mnemonic is that it's of opposite kind. So if this is I, this becomes V. If this is V, this becomes I. So this is generally true for bilateral. So this is the loop gain that has all those properties that you like. It will have the same root. It will have the same roots. 1 plus t will have the same roots as those of the delta for the transfer function, determinant of the Y matrix. So you get the same poles. And since it's invariant, it's something that you can calculate anywhere in the loop. Any questions on this so far? No. All right.
Sorry.
Yes.
Just in order to clarify, you started from unilateral loop and draw the systematic model, and you said that the transfer function between u and ui is something over 1 plus t, and then you said that this the determinant of the Y matrix being equal to 0 is equivalent for t being equal to minus 1. Actually, we saw a physical meaning for the loop gain. But here, when you have bilateral network, feed-forward and feedback, how do you know that there is a 1 plus t term in the denominator that you're trying to find that
right.
t?
So basically what I'm trying to say is that I'm going to create a t. I can define a t in such a way that I can still get 1 plus
find
t.
the physical meaning for this t.
No, the physical meaning of this t is that this is a t that would still you can map to a mathematical model of
How do you draw that model?
this. Right?
How can you draw a model for when you have both?
Right.
Your A has.
You can basically just write two loops. You can basically make another amplifier in parallel here going in this direction, like something like that, and like a prime, and you can have like an F prime going in this direction, right? You can do it. But then you have to take it into account, the impedances into account and all those things. So it makes it complicated. Now, by the way, this loop gain that we've defined is not unique. There are other loop gains that have this property. There are many functions that have this property. This one has a third property, which is interesting, is that it's easily relatable. We can relate it easily to parameters of the circuit parameters. You can define other things that can be equally valid, but they're not as easily calculated in terms of the circuit parameters in general. The good thing is that this one doesn't need to be written eventually in terms of the G's and Y's. So that's why we choose this one. But you can always, basically the idea here is to map it to an equivalent system of this. So if you were to map it to an equivalent system like this would be the loop gain. Because then, when you map it to something like that, then you can apply all the theorems and all the techniques that are developed in control theory, and we'll talk about some of them, that are applicable to this system, the black system. So the idea here is to map something to that so we can reuse those techniques. You can use the Nyquist criterion, you can use root locus, you can use Bode plot, etc., etc. Everything that you have done there is applicable. And that was one of the purposes of this course. Basically, we started from the physics, really low-level physics. So I took it from the hands of the physicists, and I will intend to deliver it to the hands of the mathematicians. Right? So you say, well, use the results of the mathematicians. So now you can connect the two ends. Hopefully, right? And that's the idea. But bottom line is that the sole purpose of this thing is to give you something that has the following property. One is an invariant of the loop. Because if it's not an invariant of the loop, then which one would you calculate? Which point would you break the loop? I mean, which one is a measure of stability? It has to be an invariant of the loop. Two, it has to have this property, so you can map it to this model. So all the theorems are applicable to that feedback system can be used here. And three, can be easily calculated in terms of the circuit parameters. But there are other ways of doing this, coming up with parameters. There are other parameters you could use. But they're not as easily calculated. Good question. Any other question? Alright? If not, let me do an example. We can do an example. Let's see how this works out. But just to give you an idea, this is typically used, most of the times, this is used when you're trying to run a simulation or something. And these are much more, these loop gain parameters, unlike the return ratio, they're much more conducive to simulation because you can break the loop anywhere you want. It can be outside the transistor model, outside anything. It doesn't have to be exactly right at the source of the transistor or something like that, or where the dependent source is. So you find a convenient place you can break it. So they're much easier to do in simulations as well. And you will do some of this stuff in your homework problems. But let's do an example. Choosing something relatively simple, at least in terms of complexity. So let's go to our single transistor shunt stage. This is R2, this is IN. And this was the stage that we have. And this looks like a simple loop. So now if I show it like this to you, if I ask you, is this a unilateral loop or bilateral loop at low frequencies, what would you say? Well, at low frequencies, if I put a signal here, would anything get back to me?
Through R2.
No. Let's say I break it. Let's say I break it here. If I apply a signal here, would anything go this way? No. So at low frequencies, it is unilateral. But how about, let's say, if you take one of the capacitors, let's say Cmu. Now, I can basically, if I break the loop here, for instance, is this loop unilateral? No, because the signal can go this way, and the signal can go this way. How? Through the capacitor. do this. Time and transfer constants. Right? So first thing, I have to determine the T, let's call it TBF0. Okay? This is when the capacitance is zero value. What is it? It's the voltage gain from here to there, which is the voltage divider ratio R pi over R pi plus R2 times G minus GM R3. Low frequency capacitor. Now, I have to calculate time constants. And well, I have to also calculate the T mu BF. When C mu goes to infinity. What is it? If C mu goes to infinity, it is shorted. Right? So if this is shorted, what is the transfer function? Well, I have an alpha Rm here. When it's shorted, I see alpha Rm of the T model, right? Because the current source is shorted, which is in parallel with R3, and is a voltage divider between the parallel combination and R2. So it's basically alpha Rm parallel R3 divided by alpha Rm parallel R3 plus R2. This is what it is. So I can basically write this as, I can rewrite it in a different way. And with a minus sign, by the way. Why minus sign? Oh, and this is plus, by the way. Because remember, there's a minus sign in the definition of the loop gain. So that minus becomes plus and this plus becomes minus. So this one is basically, you can write as minus R3 over R2 plus R3 plus R2 R3 over alpha Rm. And this one is beta R3 over R2 plus R pi. Fine. And then I have to calculate the time constant. Tau Vf for tau Vf 0. There's one time constant here, it's a zero value time constant. I don't even need that superscript 0 here. Okay. So what is that time constant? What is the time constant for this circuit? The zero value time constant. R left, R right, GM R left, R right times C mu. So it's C mu times R left, which is R2 parallel R pi, plus R right, which is R3, plus GM R3 R pi parallel R2, which again you can rewrite as R pi C mu over R2 plus R pi times R2 plus R3 plus R2 R3 over alpha Rm. You can see I'm intentionally writing it this way because this term is common among them. And when I look at the product of that thing, which is what I have in the denominator, they cancel each other out. So that makes my life a little easier. So T V F of S is basically TVF0 plus TVF mu tau VF. This is the first order system, right? S divided by 1 plus tau VFS, which in this case becomes, you can factor this out, and if you factor this out, this term factors out, so it becomes TVF0, 1 minus tau ZS, 1 plus tau VFS. And tau Z is actually relatively simple. It's Rm C mu. So that is your first order transfer function for your forward voltage loop gain as a function of frequency. So it has a 0 and it has a pole. It has a right half plane 0 and left half plane pole, as we knew already for this system. Okay, so that's one. Now we can calculate the current loop gain. So to calculate the current loop gain, I apply current source and short this one. So this is the way the circuit looks like. This is IX, R2, C mu, and then this is a short. So R3 doesn't really matter. And this is the current. I1. This is, by the way, there's a typo in your handout. So fix the polarity of this thing in your figure in the handout. It's going the wrong way. is not 0. Is 0, then C mu is not there. Beta, right? If C mu is not there, if this current is Ix, this current is Ix, this current is beta Ix. It's a transistor, right? So it's beta. What is TIF mu when C mu is infinite, when it's shorted? When it's shorted, all the current goes there. But just the polarity is changed. Well, the polarity is the same, but there's a minus sign in the definition, so this becomes minus 1. Right? And then time constant, tau IF, is going to be what? The time constant is R left, R right, but we don't have an R right. So it's R left, C mu. So it's, what is it? It's R pi, exactly. Why? Because you have to think about it. When you calculate the time constant, you know the independent source. If you know this one, this resistance is floating. So the other end of it is not connected to anything. So all you see from this node to ground is R pi. This is from the transistor. This side of it is just like a resistor hanging in the air. So it's R pi C mu. These are not easy. That's why I did those first in the hand. But so TIFS is simply TIF0 1 minus tau Z S plus tau IF, which is this S. And tau Z is the same tau Z as that, which is a good thing. Why? Why is it a good thing that they have the same zeros? Makes our lives a lot easier. Because we are adding the reciprocals of these things, right? So that forms a common denominator. You have it. And then you have to determine one reverse loop gain. So these were the forwards. So reverse. So for calculating the reverse loop gain, now I have to apply a good voltage. So I can apply a Vx here, or Vy here, sorry. Vy, and measure Vx. So what is that transfer function? Well, let's find out. So what is T V reverse 0 when C mu is 0? When C mu is 0, there's no way for the signal to get back, right? So it's 0. What is TV reverse mu when C mu is infinity? How are these two voltages related? If this is shorted, this is the same voltage Vy, and this is the same voltage because it's open. Right? So it's what? Minus 1. Because of the minus sign is the definition of a thing. And there's a time constant, tau Br, which is what? This is the voltage source. And the resistance seen by this guy, so it's shorted on this end, because it's the source. The voltage source doesn't, when null, it's going to short this to ground. This side, what resistance do you see from ground, from this node to ground? R pi. So it's C mu R pi, which is equal to tau IF. Right? Okay. So now you can basically calculate the reverse voltage gain, TV reverse of S, and that's basically, since this term is 0, it becomes minus tau IF 0S over 1 plus tau IF 0S. So which makes sense. This is a transfer function which goes to 0 at low frequencies. There is no reverse loop gain at low frequencies. But it's supposed to be fast. Okay, fine. And then you can now calculate the whole thing. So basically you say 1 over T f of S is going to be 1 over TV f of S plus 1 over T I f of S plus hand out too. I get an expression, and for large beta, so basically the expression for general beta is there in your handout, so it's a relatively long expression. And for large beta, just to see what it is for large beta, this becomes what it is. That expression, the original expression also, has one pole and one zero. So, and so does this one. So this becomes Gm R3, 1 minus Rm C mu S, divided by 1 plus R2 R3 plus Gm R2 R3 C mu S. So this is your loop gain. Now, if you want to do stability analysis, etc., we can use this expression for calculating our stability properties of this loop, and etc., etc. So, the point is that now this is invariant. This doesn't matter where you bring it. Now, an interesting point. We set all of these things for a single loop. Now, if you have nested loops, you have to be careful. So let's think about it, and we'll talk a little bit about this later. So let's say you have blocks like this. So let's say you have a system. Let's say A, B, C. Let's say they're unilateral. Then you have a D going back here, tracking from this guy. And then you have an E. Like that. So this is your input, this is your output. So if I ask you, what's the loop gain of this thing? What would you tell me? Which loop? Yeah, right? We have two loops here. We have this bigger loop and this smaller loop. So now it's getting interesting, right? More interesting, and it gets more and more interesting the more things you add if you run into a situation like this. Now, if I break, you have to be careful depending on where I break it. I get different things. Now, if I calculate loop gain in a circuit, and if I really break it here, there, or there, I should get the same loop. That's the loop gain of the this bigger loop, including this one. So basically, what that means is that you're thinking as this whole box, whole combination, as a box with a transfer function of b over 1 plus bb. So this is a new, we are abstracting it as a new box. And if you do that, you will see that the loop gain of this thing would be basically this times that, divided by this, by 1 plus this times that times that. So this becomes your new A, and this becomes your new F. Now, but you have to be careful. Actually, if you go and break the loop there, or there, then you will get a different loop gain. You've broken two loops. Well, it depends. And actually, here you've broken two loops. Here you've broken one loop. So actually, you get a different thing here than there. So if you break it here, you will get a different quantity. If you break it here, you will get a different quantity. And if you break it at these places, you get a different quantity. So that you can do in circuits too. Think about it. Even in this example, I could have broken my loop here. And had I done that, it would have been equivalent to breaking it here. That's basically what we color-coded consistent. It's equivalent to that. Or, had I broken it here, that would have been equivalent to breaking it kind of here. So, I will get a different loop gain if I do it that way. Because I'm not dealing with a single loop anymore. Now, there are general criteria, and we'll talk a little bit about it, about how to determine the transfer functions, and how to deal with this, and how to talk about stability of these things. And determination of these things are interesting. I mean, these are okay. These are nested loops. Nested loops are not that difficult. When one loop is entirely within another loop. Because what it means is that you can basically abstract it away like that, and you can treat this whole system as a new system, and say, okay, I want this system to be stable. And then if you really want to be careful, you can say I want it to be internally stable here and externally stable there. So you have two sets of loop criteria that you need to apply to make sure that it's stable. So you have to make sure that this is stable by itself. So you apply your stability criteria to it. And then you take this and say, well, this is a lump system. If it's, it's the box abstracted away and say, I want to make sure this is stable. Now, they can be a little bit more naughty. How? Think about it this way. Something like this. Now what do you do with this? No. So you can actually treat this, again, there are techniques to deal with this, and it's really starting to get into the control theory. As opposed to circuit theory. Now, the good thing about the loop gain, the way we define it, is that it allows us to directly relate our circuit quantity to things like that, and then apply the techniques from control theory. So these loop gains, the way we define them, are consistent with what you see in those models, control theoretical systems. And you can use all those techniques. We can talk a little bit about it next time we talk about Mason rule and all those things. We can talk about how you determine these things. Right? Any questions? Yeah.
In
This one?
that example, we could have another loop consists of A, D, E, and C. Yes.
A, D, and C?
A, D, C, and C.
A, D. Do you mean this?
Yeah.
Okay, well, no. In this box is the way I've driven them. I'm assuming that these are unilateral. Oh yeah, if you have bilateral.
I wanted to ask if you exclude from the stability of the smaller loop and the bigger loop, the stability of the loop that is subtraction of those loops.
So say again, what's the question again?
Can we conclude the stability of the loop that consists of subtraction of two loops from the stability of those two loops?
Yes. If the two loops are independently, if the nested loops are stable individually, and if they're nested like this, then that's one special case where the difference loop is going to be stable. But in general, it becomes more complicated than that. There are ways to calculate the loop, relate the loop gains of inner loop and outer loops, equivalent of a Mason rule, but for loop gains. But it just becomes too complicated. So what people do is basically just break it down into smaller pieces as much as they can. Now, in circuits, part of the reason, and it's like a chicken and egg thing, you don't see a lot of these kind of things. You see nested multiple loops, like nested Miller compensation and things like that. But you don't see a whole lot of stuff like that, crossing loops. Why do you think that's the case? Because it's hard to analyze these things. But you design your own circuits.
Oh, I see.
So it's a chicken and egg thing, right? So people don't design things a lot. There are few examples of this. But that means that if you apply some of these techniques to your design, you can come up with circuits that have not been used before because people didn't know how to deal with them. But then you can do things that people couldn't do before. That's the beauty of circuits. I mean, there are a lot of things that people haven't